Let's tackle LeetCode 572, Subtree of Another Tree. You're given two binary trees called root and subroot. Your job is to figure out if subroot appears as a subtree somewhere inside root. A subtree means you pick a node and take everything below it. The structure and values have to match exactly. Return true if subroot exists as a subtree, false otherwise. For example, say root has nodes 3, 4, 5, with 4 having children 1 and 2, and subroot is just 4 with children 1 and 2. Starting at the node 4 in root, everything below matches subroot exactly. Same structure, same values. That's a valid subtree. The obvious approach is to check every node in root and ask, does the subtree starting here match subroot? At each node, you'd compare the entire structure. This sounds expensive, but let's break down how it actually works. This strategy uses two functions working together. First, a helper function that checks if two trees are identical. Two trees match when their root values are equal and their left subtrees match and their right subtrees match. If either tree is null, both must be null to be equal. Second, the main function traverses root looking for a match. At each node, it asks three questions. Does the tree starting here match subroot? If not, is subroot somewhere in my left subtree? If not, is it in my right subtree? Return true if any of these succeed. Let me walk through an example. Root has 3 at the top with 4 on the left and 5 on the right. Under 4, we have 1 and 2. Subroot is 4 with children 1 and 2. Start at 3. Compare 3 to 4. Values don't match. 3 is not 4. So the tree starting at root doesn't match subroot. Check the left subtree, move to node 4. Compare 4 to 4. Values match. Now check left children. 1 equals 1. Both have no children below, so left subtrees match. Check right children. 2 equals 2. Also no children below. Right subtrees match. The whole thing matches. Found it. Return true. Now what if subroot wasn't in the tree? Say subroot was 7 with children 1 and 2 instead. Start at 3. Compare to 7. 3 is not 7. Check left subtree. Move to 4. Compare to 7. 4 is not 7. Check 4's children. 1 is not 7. 2 is not 7. Back up. Check right subtree of 3. 5 is not 7. No more nodes to check. Return false. Time complexity is O of n times m. We might visit every node in root, and at each node we might compare up to m nodes in subroot. Space complexity is O of n for the recursion stack. In a skewed tree, the call stack could be as deep as the number of nodes. Found this useful? Master key interview patterns at AlgoMonster and land your dream job.